Hello, dear colleagues. Let's start our presentation. Welcome to Dublin. My name is David Gilnazarian, and uh, let's talk about combined heat compute and liquid cooled solution. So first of all, let's start evaluate what we have inside of the center. And we have a building and racks. And let's compare the carbon inside of this component. So let's assume that we need 3 cm per rack, and we have 40 servers in one rack. So carbon of the building will be 3 metric tons, and the rack 40 metric tons. But the lifetime of the building is 30 years, and the rack lifetime is average 3 years. So during this 30 years, the carbon of the building will remain the same, but the carbon of the equipment will be uh, for 99%, and the building much less. So this is why it's very important to focus on the circularity of the IT equipment. Another thing is about the energy consumption of the IT equipment itself. So we can compare a GPU servers. On the left, you can see air-cooled server, and you see that among the overall energy consumption, fans energy consumption is 2 kilowatt, and power supply unit provide all that energy for all components. On the liquid cooled, we have the same amount of the IT components, and this part is liquid cooled, but that allow us to reduce the energy consumption for the fans, which cover only this part of air-cooled components. And that reduction overall allows to reduce also the power supply and energy consumption. So overall, we reduce from 11 to 9 kilowatt. Another thing is about servers and rack level decarbonization. So by shifting from OEM to OCP servers, we can take away 4 fans on each server level. We can take away the power supply units because we have rack level power supply shelf. We take away another two top of row rack switches. Take away power distribution unit because we have centralized bus part. And we take away cranes because we create new conditions for the servers. And we take away all unnecessary strips, cords, and etc. So another thing is about the AI cluster. So here you can see 24 rack air-cooled cluster. And the idea is to shift from 24 to 2 racks, where each will be 200 kilowatt. And how to do that with industrial approach in big scale. And this is the role of OCP, that you can see evolution of OCP rack from ORB2 to ORB3 NVIDIA. And on the top and bottom, you can see power shelves, 4 of them, each 50 kilowatt. So we have 200 kilowatt working, 200 kilowatt reserve, and also much densified GPU blades and switches. Also, you should think about the how to take out the energy, the heat, and you can compare air performance, water-based liquid cool solution, and two-phase on-chip cooling. So when we have AI dedicated racks, we have a huge flow, like 350 liter per minute, and in that case, we need a row-level CDU, which will cover all the racks, and we will not spend the space for the CDUs because we have this big flow rate. It will take too much space. And if we shift to two-phase, then in this case, we can have rack level CDUs. And also, we can simplify the data center design itself. This is the traditional data center design. If we shift for the OCP racks, we can have much higher inlet air that allow us to take away chillers and cooling towers. Also, we can have on rack level a power shelf with battery shelf, which allow us to take away centralized UPSs. And overall, power input for the data center is reduced, and that may also impact on the gensets, which provide the overall energy for the data center. This is the way of decarbonization on facility level. And also, I want to talk about the densifying and having the less carbon on the building level. So here you can see two modular open source data centers. On the left, air cooled, and here is the limit is indoor coolers. We have three working, one reserve. Each indoor cooler can provide 30 kilowatt, so overall 90 kilowatt. This is the limit. If we go to the AI dedicated racks, we have door heat exchangers and on-chip cooling, so we can achieve 100, 120 kilowatt per rack, and 16 of them can form 1.8 megawatt. So this is how we can reduce up to 20 times the surface for the our data center. And another thing is about the heat reuse. So usually data center goes where the land cost is low, energy cost is low. And after start to think about heat reuse and realize that there is no one in neighbors, or you need to invest a lot of money for this piping to get to be connected to the grid and district heating grid. And from that perspective, we created underground data center, which allow us to bring 3,250 racks close to the users. We need just a shaft space 10 on 10 meters, and we don't touch on ground buildings, and create this space underground. And in that case, we have designed a row of racks with on-chip cooling, with door heat exchangers if it is only air cooled, and these subsystems, and they are connected to the facility loop, which provide the hot water to the city. In that case, it's important to have flexible design when we can start with only air-cooled racks with 1 megawatt for 75 racks with this flow rate and these temperatures. And after that, shift to the liquid cooling and have 3.7 megawatt, but the same flow rate. And this we achieve with the on-chip cooling. And the same on facility level. So we can have 45 megawatts. This is the flow rate. And we can achieve 162 with the same flow rate by playing with the temperatures. And in the end, I want to say that it's important to understand business demands, which define the software demands. Software demands create server design, and we adopt that for liquid cooling, including the rack design adaptation and facility design. And after that, of course, we should think about ecosystem. In that case, you see the fish farming connected with the greenhouses, which produce algae, food for fish, or many other applications, including for Ireland. Thank you very much for your attention, and I'm passing my presentation to the Stefan Frenzel. Thank you very much.